Hi, everybody. I just want to take a moment before we get started with Tom's second presentation titled ARLISS, a rocket launch for international students' satellites. I want to remind everyone, feel free to use the chat as much as you like to converse amongst yourselves, and then just make sure to put all of your questions in the Q&A. And then at the end of it, Tom will go over and click on Q&A and be able to answer your questions. But please just put your questions in Q&A in the chats for talking amongst yourselves. Thank you. Go ahead, Tom.
Thanks, Todd. As in my previous presentation, I wanted to thank Todd for his time he spent with me yesterday getting these computers all synchronized to be able to present. I ran into a couple of glitches on my first presentation because I originally did the presentation in a keynote on an Apple, which wouldn't work with Excel events. I had to convert it to PowerPoint, and there was some configuration problems. So hopefully we won't experience much of that in this. Anyway, my name is Tom Rouse, and I've been a longtime Rocketeer. I started the ARLISS program in 1999 with a group of people. I met Professor Twiggs at Stanford University. I was involved with, well, naively, I was going to try to launch a rocket to space during that, it's called the CATS Prize, Civilian Access to Space, where the Space Frontier Foundation put up a $250,000 reward to the first person that could launch a rocket to 60 kilometers, I believe it was. And so I said, well, if we're going to launch a rocket that high, let's put a payload in it. So I contacted Stanford. I live in the Bay Area, and met Professor Twiggs. And he jumped at the opportunity because in the past, these universities had been building huge, grandiose satellites and with no chance of ever launching them. And you would have a group of students that would build it one year, and then the next year, another group of students would come in, and there was no history, there was no handshaking going on. So it was very difficult. So what they did is they started building smaller satellites and testing them by putting them in garbage cans, tied to ropes, and throwing them off balconies for shock testing and swinging around their heads. And they had no way of really testing these things real life. So during the discussions about going to space, he said, well, geez, you're a part of a rocketry club, amateur rocketry, NAR in Tripoli. And do you have a way to launch these satellites for us? And at the time, the satellites were called CANSATs. There were some symposiums that Professor Twiggs had gone to, and they all discussed amongst themselves, other universities, let's get a commonality. Let's get a common size. Let's get something where we can all use the same database to compare results. So they concluded and arrived that everything should go into a can, like a Coke can. So that was the form factor. And then they specified a weight. So that was what they said we're going to all share. Everything has to go in that so we can get the same results. So these were what we launched at the beginning. And it was called a rocket launch for international students' satellites. And students from all over the world were building these satellites to go into these Coke can size things. I wanted to thank NAR and John Hockheimer for being a very active and avid supporter of ARLISS. And NAR has taken over the ARLISS support and been instrumental in our success and operating this international competition from universities from around the world. So thank you so much, John, and thank you so much, NAR, for your support in this and being involved. It's a wonderful, wonderful program. It stands for a rocket launch for international student satellites. Okay, now we go out to Black Rock Desert, and every September, the end of September, is where it takes place, which is kind of a drawback for the American universities because their curriculum, they're out of school in September. So we don't get very many, if any, United States universities. But here is, these ARLISS rockets are M motors. Aerotech M1419 is the motor that's used. And they go about 10 to 12,000 feet. So you have all the same altitudes. And like I said in my formatting, you guys, I'm sorry. This is just not wanting to play the video. All right. So in the beginning, we had the cheap access to space. I went over that. The CATS Prize was 1997. and the Space Frontier sponsored that. Here's Professor Twiggs out at Black Rock, and this was one of our first rockets. And this rocket was based upon a black sky. Do you all know Scott Bartell? Scott Bartell had black sky, and he made this rocket as a kit. And originally, this rocket was being used by NASA to test rapid access radar tracking. So Carl Bauman and Pius Morizumi and William Walby would go out into the desert and launch these rockets at a 45-degree angle. And the NASA radar would try to track it. So obviously, these rockets being launched at a 45-degree angle would get trashed. So the Scott Bartell designed these rockets to have components. Nothing was epoxied, it was all mechanical. So you could crash the rocket and come back and take out all the parts that were still good and put it into a new rocket. So the fins were bolted on and everything was bolted on, so you didn't have to trash the whole rocket. The first people in ARLISS the first year was Jim and Becky Green, William Walby, Pius Morizumi, and Randy Mitchell and his son. They were the first people to launch rockets for Stanford. Here is a CanSat with the 3 cans in it, and this is a 6-inch rocket, so this is what we call a carrier. And these, when you call them satellites, they're not going to space, but what they do is we put a parachute on it so it stays in the air about 10 minutes. The hang time is 10 minutes. And why is that 10 minutes important? Because that is basically what a satellite in low Earth orbit you'd be able to receive a signal when it comes up over the horizon and when it goes down over the horizon. You have about 10 minutes of communications time for a satellite in LEO. And so we hang it 10 minutes. So it would simulate a real LEO pass. And the satellites would all get ejected. And in the beginning, these satellites would be, cameras, heat, whatever. And the challenge was to get them to turn on automatically, like a real satellite cannot be operable when it's in the rocket. So these things have to turn on when they're deployed. They have to come down and they have to have telemetry. And that was in the beginning in 1999. So there's a picture of myself on the right and William Walby, one of the first ARLISS rockets the first year. And these are the original people in ARLISS. And this was 20 some years ago, 1999. This one here on the right is a CanSat. And you can see this one has a GPS in it. Here's the GPS. So this one was obviously it was transmitting GPS telemetry back down to the ground. And you can see how old this is. Look at the batteries. They're not lithium ion anymore. So this was probably 1999, 2000, 25 years ago. So that's why they have the nickel metal hydride batteries. You can see these components and it'll tell you when it was built. Then the CanSats evolved, and all of the universities says, hey, what we want to do is we want to have rovers. So when they go to Mars or when they go to a planet or when they do something, the challenge is to have a GPS recorded point on the desert. So we go out into the desert and we record a point and we give it to the students and they program it into these rovers right here. And when it lands, it has to disconnect its own parachute and it has to say, where am I and where am I going? And it has to navigate back to the point we give them. And we put a flag in the ground. And so they try to navigate back. Pretty sophisticated stuff from these students. In 2000, I believe, maybe it's 2002, UNISEC was formed because the success of this and the complexity of the comeback, they call it the comeback with the open class rovers, to be able to come back to the flag, was so high tech that they formed this. And UNISEC also supports these students to build CubeSats. And to this date, they've got dozens of CubeSats out there in space. And the foundation of all of these projects, when they evolve to go to space, has been the ARLISS program. So NARA is involved with supporting students baby steps into going to space. This person right in the middle is Professor Shinichi Nakasuka. He is the one that started the ARLISS program, the international program with Professor Twiggs. What has Bob Twiggs meant to the ARLISS program and our rocketry? Okay, Bob Twiggs is the father of many, many, many things. He started ARLISS. He was the inventor of the CubeSat. Do you know that CubeSat has just gone on to be an incredible success? It is a company, it has started out a company called Planet Labs, who has gone public, and their sole purpose is to send CubeSats into orbit and take pictures of the whole planet. He has started up orbital satellites businesses, and which eventually came Planet Labs. So ARLISS, CubeSat, and Planet Labs. So this is pretty amazing that somebody has started these things, which has evolved into be international successes and the basis of forming companies that go public. The people that have supported the ARLISS program over the past 25 years has been Aerotech, Gary, Dane, and Carl, by delivering motors and offering the motors at a discounted price for these students. They could have made more money, but they have been a real champion in the support of this educational process. These are the flyers. So the universities come from all over the world, and we have people that have to build the rockets and fly them. So the current flyers, you can see on the left, there's quite a few people that show up out in the desert, build their rockets and fly them. There's a lot of past flyers who have moved on. And for the NAR group, we owe a special thanks to John Hockheimer and John Lingdahl. They've been instrumental in getting NAR to be the main sponsor of this. Quote unquote, the Washington group and the Oregon gang. You guys are great. Thank you so much for supporting ARLISS and coming out to Black Rock Desert. Dave Raimondi. Dave Raimondi was the, I guess you would call it, president of the NAR section here in the Bay Area for 20 years or so. William Walby, Becky Green, and Jim Green. They're the ones that make it all happen. So thanks to all them for all the work they've done and do. So look at the universities that attend ARLISS. It's pretty amazing. This is not a small undertaking. And I'm sorry again for the problems with this layout. That's the conversion from Keynote to this PowerPoint. But you can see there's all over the world. You got Japan, you got San Luis Obispo, Eugene, Oregon, Peru, Reno, Kentucky, Hawaii. Jake is a great guy, Montana State. This is a big program. And it would be really nice to see more NAR flyers build these ARLISS rockets and come out to the Black Rock Desert and represent NAR as being a flyer for these. If you want to contact myself or Becky Green, she is really active in NAR. We can get you the information to build a ARLISS rocket, and you can come on out, and the motors are free. You can launch these rockets and participate with all these universities, which is a kick. So here's the con ops of an ARLISS rocket. Concept of operations, for those that don't know that. You've got your boost, you got your coast, and you got near apogee, it arcs over. At apogee, you have a separation, okay? It separates into two sections. The booster continues to come down, and we size the booster parachute so it will match the descent rate of the payload. So the payload has its own parachute, and why? Because so that the payload can hang down and the nose cone can be pointed down when the nose cone comes off. Why? Is so that way the payload will drop out. If you had the nose cone come off at apogee, if you had the nose cone come off at apogee, I don't know if the payload would drop out. And apogee plus 6 seconds is when the ejection charge fires and fires the nose cone off and the payload comes out. So then you have the 3 parachutes of those independently coming down. So the parachutes are all sized so that your landing, your dispersion zone is kept to a minimum, so you don't have to go searching for all of these components when it comes down. Now you're going to get a quiz on this. Not really. But apogee is 10,000 feet. Remember this. Maximum descent rate is 18 feet per second. So calculate the time in the air. If you're at 10,000 feet and you're coming down at 18 feet per second, how long are you going to be in the air? What's your drift with a 10 mile per hour wind? And what's your drift with a 5 mile per hour wind? So I don't know if a lot of people do these calculations because you're on smaller fields or what, but when you're out in Black Rock, these things are important. Actually, it's important anywhere you're at. Do these calcs. They're pretty simple. It's just elementary stuff. The answers are 9.2 minutes in the air for a descent rate at 10,000 feet. It's quite a bit. The drift at 10 miles an hour is 1.5 miles. The drift at 5 miles an hour is 0.8 miles. That's quite a bit. So it seems odd when trying to come back to a point of launch. So none of these, what I'm trying to point out here is, I got confused, I'm sorry. None of these satellites has attempted a phased descent. So if you're gonna go up to apogee and you're gonna drop out and you're gonna have to land and come back to a certain point, if you're gonna drift 1.5 miles, and 10 mile an hour wind is commonplace out there. If you're gonna drift 1.5 miles, that's a long ways for these little rovers to go. So why don't they try? And I would recommend, if you're going to do this ARLISS stuff, a phased descent, a drogue in a main, or reefing, or a streamer in a main. So that way your satellite can come on out and get a lot closer to the flag and have less terrain to cross. It seems odd to me that they don't try to do some kind of a phased descent to get your landing closer to the flag. The standards for the flyers and the participants, you all have to have the rules, and the rules for the flyers, the rocket designs have to be similar. That has to be the same con ops. Recovery has to be the same, use the same motor, and your rocket can be either fiberglass or carbon fiber. The participants, they have to have their form factor. All right, they have to be able to fit inside of the carrier, which is 11 7/8 overall. I think it's about 10 inches inside. All of your satellites have to be off, turn on automatically when they're ejected. And the design standards, they have to live up to the design standards of the competition they're in, and their descent rate. So these are some of the designs that they have to all adhere to. The wireless communications, the CANSAP shall stop transmitting radio waves except for permitted devices while it is mounted on a rocket. So that means it has to be off at launch. These are some of the rules that they have to conform to. And CANSAT shall be trackable and locatable all parts. So they have to have their own GPS on it. I'm not going to go into this too much, but you can see that the UNISEC rules, they have page and page and page of regulations. One thing they pay attention to is the opening shock force. I don't know if you noticed on one of the earlier CANSATs, there was a small string attached to it for the parachute. They didn't do their homework on what the opening shock force is on a parachute when it's coming down. If your apogee is 50 miles an hour and 6 seconds later your parachute comes out, you could be going fairly fast, and the opening shock force on the parachute could tear your satellite apart. So they have recommendations. The shock load you can see on the bottom is 50 Gs. So they have to design their satellites to a shock load of 50 Gs. Some more rules that they adhere to. And what's interesting is the data used are current. This is transferred from Japanese to English, so it's very hard to read and understand. But basically what it's saying, when it gets onto the ground, it has to use a magnetic field sensor to figure out the direction they're at, north, west, south, or whatever. And then it figures out where it has to go to the flag. And so this is some of the programming logic they use. The control history is 11, 32, and 10, 11, 32, and 40. So they'll go 30 seconds, say, where am I at? And they'll do a certain direction. They'll stop and say, where am I at? And then they'll go another 30 seconds. So they might change their 10 degrees, and then they might change it to 5 degrees, 2 degrees, minus 3 degrees. So every 30 seconds, they will do their modifications. So go left, right, or whatever to get to where they're at. But they start out with a magnetic field sensor to know which direction they're going. One thing is, you see the at the top where it says apogee plus 6 seconds, the nose cone and the payload comes down. So you have your payload, and the parachute on the payload has to be larger than your descent rate, and the parachute has to be larger than the nose cone and the payload. Why? Is because if the payload's coming down faster than your two items below it, it could run into it. All right. So you need to do your math and you do your homework and make sure that your payload that's going to be above remains above, which leads us to an interesting project we were working on. It's for the IPPW. It's called the International Planetary Probe Workshop. And San Jose State wanted to do a analysis of collision avoidance. And they did a presentation in France. This is held all over the world in different places each year. And it's pretty interesting because if you have, for example, if you're landing, a lander is coming down, and I'm going to use Earth numbers at 75 feet per second. Let's just say you're going down to Mars. And it's going to land and it's going to go to try to find water or whatever. Well, when it lands, it's going to have to go searching all over the place. So why not drop some scout satellites? Okay, 3 or 4 or 5 or 2. And so you have a dispersion pattern. So these scout satellites can communicate back to the main lander and say, hey, I found something here. So it doesn't have to go searching forever to find things. So the problem is, if you're coming down at 75 feet per second and you drop these satellites out, like an ARLISS satellite, but these are going to start open up at 20 feet per second to land. How do you keep that upper lander from hitting the lower satellites? So we're doing documentation, and it'd be really nice to do some documentation on the ARLISS rockets with some video cameras to film the payloads dropping away and how they open, and from the payload looking up at how that works for the rocket. So when you're doing some rocketry, and I just wanted to point this out, a little bit of calculations, a little bit of information is kind of fun to know. If you have your design criteria is 9-pound payload, and this is a calculation of how fast is this going to go after 6 seconds. If you're coming down at 75 feet per second and you let it free fall for 6 seconds, how much speed is it going to gain? And you can see right, the calculations start up at the top and they go all the way down. And here's your answers. After 6 seconds, you start out at 75 feet per second. In considering drag, you end up with 208 feet per second. The shock opening force is 1,598 pounds. So in 6 seconds of free fall, 9 pounds, you're going to be accelerated to that. So keep that in mind when you're designing rockets and you have apogee plus 6 seconds or apogee plus whatever. The speed can really be violent, and your swivels are rated at 1,500 pounds. So these are some calculations that I just thought it was amazing. One of my students did this, and it was an eye opener at just how much you should pay attention to your opening forces and your speeds. This is similar to the ARLISS. This is a parachute opening, and it shows about 2 seconds, okay? And I can't go back on this, but what it is it's a red pilot parachute, just like the ARLISS, payloads. When they come out of the carrier, the parachute's on top. How is the parachute on the top going to catch air? Because it's on the top, it's in the vacuum, it's in the backdraft. So getting that parachute out is really important. And this is a method of using a pilot chute in a deployment bag, and it pulls the parachute out of the tube. And so we wanted to test to see how long it would take for that to open, to be able to correlate that into how much velocity was going to be added to the there you go. There's the pilot, pulls it out, 2 seconds. So there you go. Testing, you guys. Testing is fun. It's a blast. And do it as much as you can. I don't know if you've ever been to Black Rock Desert, but there's a picture of Black Rock Desert. Just a beautiful, beautiful place. And this is, on the right, that is your comeback. This is a spot in the ground that they put a cone and a stick, and they record the GPS coordinate and give it to all the students, and they have to land there. And you can see how big this desert is. That's why we were thinking, why don't they have some kind of phased descent so they can get closer to this flag? If the rocket goes off, arcs over and goes a mile or a half a mile to the left, and then it drifts a half a mile to the left, you're 2.5 miles. And I don't know whether these rovers can make it back. They don't have great luck. I think each year, out of the dozens and dozens of teams, there's only one, maybe two that get back to the stake. All right. This is one of the first CanSats, and I showed this to you earlier. You can see the switch that's hanging out of the right is loose, I don't know, and there's the blue cord that was used for parachute. Definitely not going to withstand the forces. When they started doing the comeback, the students thought, well, let's try to get back to this pre-recorded GPS coordinate and have a steering parafoil. That seems logical. I would think that would be the first reasoning before you would get a rover. But they started experimenting with steering parafoils. It never worked. And I'll tell you why in a minute here. Here's another steering parafoil. Look at the complexity of the lines. This one obviously has a camera on it. You can see the camera there. And lots of parachute lines, and they didn't work. Why? Is because if there's any kind of wind whatsoever, they couldn't steer into the wind, and they would end up going in circles like you're sailing a boat trying to get back into the wind, and they would just corkscrew basically away from the target, or just corkscrew with the wind. They couldn't overcome the force of the wind blowing them sideways. I think what you would need to do is have a descent rate faster to get into the wind. But anyway, it didn't work, and they scrubbed it, and they started this. So this was the design of the 2005, and similar to a tank. They thought, well, the Black Rock Desert is full of ruts and dirt and clods, and so we need to navigate. It's not a smooth pool table surface. So they came up with this. Do you see the problem with this? Do you know what a turtle is? What if this thing lands on its side? It's just a poor design. It's a great design, but you're assuming that it's going to land flat. So what they do is they came up with this, fold out wings, so it doesn't roll onto its side. You can see the GPS antenna on the top. These didn't work. So they started with parafoils, and then they started with the tank type of design. And boy, did they evolve to this. And when we first saw these, we thought, what the heck is that? These things work like a champ. And this was one of the earlier ones at the design. And I don't know how they kept it from just spinning, but they did evolve. Here's another one. And they have a tail on the back. So when the wheels turn, it keeps the carriage flat. They have to have some way of stabilizing it. Here's a really nice one. You can see a great picture. You see the triangular piece on the bottom. That keeps the carriage from spinning when the wheels move. And so it drags on the back, and then they can turn right, left, or whatever. GPS is on it, and you see the yellow wire on top? That's a no-no. These have had failures from just all kinds of crazy reasons. Wires have broken. They've gotten snagged on something and pulled out. So there's no strain relief on that wire. It's a fantastic piece of work. A chain is only as strong as the weakest link. You can get myopic and try to do perfect work on one thing, and you leave a little loose end on something else, and your whole project is trashed. So that's what makes rocketry so interesting, is you just can't have any loose ends. Here's another one. Now this one is pointed in a different direction. Notice the ground clearance also. They started learning that you can't be dragging onto the dirt clods, and they get stuck. So this one's in a different configuration. The GPS and the antennas are on the top. Okay. During my classes at San Jose State, I show pictures of what not to do. So I don't know whether it's a good thing or not, but the aluminum wheels are heavy, okay? And you can notice that they have some real high-tech string on there. I don't know where they got it, but it must be really, really high-tech because they're using it in this satellite. There's a plastic bag, which I'm assuming it must be mil-spec because it's on a satellite. And it's really close to the ground for when it's going super fast. It reduces the aerodynamic drag. So this is an example of what not to do. I'm being facetious here, but if you were grading this project, what would you give it? Here is a launch. And a landing. Amazing, huh? It was encased into a, look at that. Absolutely amazing.
うわ、電波がまずい。これ、
It's trying to figure out where it is. It doesn't have any idea of these ruts.
ああ
Look at this.
あれあくそ、ここでもしかして終わりか
They've got it programmed to understand that it's stuck. It flips over.
おいおいおいおいおいおいまさかの展開かおいこれ
You just want to reach out and help it, don't you? That's pretty exciting, isn't it?
嘘もう絶対ダメだと思ったよあ
Look at that. That's absolutely amazing, you guys. Very, very difficult. Each year, there's only one or two out of dozens and dozens of teams. That was not easy to do. These students go on, like I say, and they launch real satellites to space. The overachievers of the group was this group right here. And thank you to Becky Green and Dave Ramoni for getting those videos to us. Let me see why. Here it is again. Oh, here's another one, you guys. This is it lands on the ground. Oh, parachute pulls it off. There you go. It's figuring out where it is. Unfortunately, you guessed it. A whole year's worth of work, traveling from Japan, having everything be successful, and it gets tangled in a parachute. What are the odds? It's amazing stuff, though. That's it. Here's a picture taken by John Wilkerson. John Wilkerson is a friend. He's always out in Black Rock. He goes to a lot of NAR events and photographs rocketry. If you get a chance, go say hi to John at some of these launches. He's always around. Here is the student responsible for that successful. And I have some Japanese friends, so I asked him to comment in Japanese. I don't know if there's anybody here speaking Japanese, but this is what he has to say.
東京都立大学の伊藤翔馬と申します。私たちのミッションはゼロメーターゴールを達成することです。で、
You
ま
can
だ
see
ま
Carl
だゼロ
Bauman
メ
in
ー
the
ターゴールを達
background
成したチー
in
ム
his
は
Aerotech
4
tent.
チームしかないので、今回東京都立大学でも達成できるように頑張っています。はい。
So much fun out in the Black Rock Desert. You guys need to get involved. Okay, Dave Raimondi, Mr. Conehead. He's a close friend of ours and one of the biggest supporters of ARLISS. Lives in the Bay Area and goes out to the desert. He's the past, I think he was in charge of the NAR chapter here in the Bay Area for over 20 years. Very active in supporting NAR and TARC and anything else that has to do with rocketry. So Dave is a wonderful guy. Becky Green. Becky Green was one of the people that started ARLISS with me. And she has taken over and run this thing solo with Dave's help. And there's other people, obviously, but they've done the lion's share of the work for 20 years. And they deserve a big thank you to all of the work that they do to keep this international organization going. This year, I flew a rocket. This is an ARLISS rocket from the University of Mexico. And these guys had so much fun. They were very, very impressive. Probably one of the most impressive teams out there. On the left is Gerald Mukes, and this is the video of one of the students talking about
University, Campus Tijuana, all the way from Mexico. Yeah. His name is Jack. Jack's mission is to go to a specific set of coordinates that are going to be, well, they were already sent to us from base. And our mission is just to get to them with the GPS and just with no intervention, like it's like a space mission. So yeah, we're ready for blast off, please. You do the camera down and push the button. The right one? Yeah. Okay. Blast off in 5, 4, 3, 2, 1.
Okay, so I cut that. This is a ARLISS rocket, is 6 inches in diameter, weighs about 44 pounds, roughly, depending on their payload. At liftoff, uses an M1419, and this one went about 10,400 feet. The rockets will usually go between 10,000 and 12,000 feet, depending on the weight of them. But here's a typical ARLISS launch taking off. Lots of fun.
University.
Okay, I'm going to show you some flight data from an ARLISS rocket. This is a San Jose State rocket I built with my team in 2008, and they participated in ARLISS for 1 year. Here's an ARLISS rocket, is 6 inches in diameter. They're about 9 feet 6 inches. They have 4 fins. They're all bolt-on, removable, and they're sheet metal. They weigh about 50 pounds at takeoff. This one had GWiz flight computers, and we always take off at Black Rock Desert is 3,900 feet above ground level. And so the simulation you're going to see is based on 3,900 feet at 90 degrees out during the day. And I had a 6-second delay. So I don't know how much you guys get into analyzing your flight data after a flight, but I just love it. I think it's like a crime scene. Everything is there, all the clues, every single thing. So let me go over this with you. Here you have the thrust, and then you have burnout. And right here, the motor burns for 7 seconds. Why would you have deceleration if the motor was still burning? It's because the thrust of the motor after about 5 seconds is about 150 pounds, okay? That means that the drag on the rocket at that time is more than 150 pounds. And if it's going about Mach 0.8, you can easily see that you would have 150 pounds of drag. That's why you're not getting any acceleration when the motor is still burning. But here's the deceleration. Here's the area of deceleration, and here's apogee. Okay, you have the spike, and then you have all this stuff happening here. What is that? Well, this is the shock force of the parachute opening, okay? And this right here, it shows acceleration. Why is that? It's because the ejection charge shoves the payload apart and accelerates it. So you're slowing down, but then you have the ejection charge going off right here, and you can see that it accelerates the payload, and you get it recorded as an acceleration. And this is the parachute opening. You get your big negative G. It's over 20 Gs of opening shock force. All right, 6 seconds later, boom, here is the ejection charge separating the nose cone and the payload coming out. So all the clues are here, and I just love watching that. So if you ever have any problems on your rocket or something, this doesn't lie. This is all the clues. It's fun to go over your accelerometer and your baro data after a flight. Here's the integrated airspeed. So at that 5 seconds, we were going 1,000 feet per second. So you know that the drag is pretty high on that. And that's why it was slowing down before the motor thrust stopped. Here's a many thanks go to Jim Wilkerson for all his photography. This is a wonderful shot of Jim that Jim took of somebody's rocket. Pretty impressive. And an overlay graph. This is the summary of an M flight. This one was 11,000 feet, maximum airspeed. It almost went Mach. So all of this stuff is fun to get. Here's some more shots of ARLISS rockets taking off that Jim Wilkerson took. This one is Dave Ramondi's, the pencil, and you can see why. Now he uses a conical nose cone just for looks. I don't think there's any other reason. And Jim, when he takes pictures of these teams, he has them all jump. And this is a team from Japan having a blast. Some more pictures of Black Rock. Those are the Calico Mountains in the back. And the reason they're called the Calico Mountains is they're all different colors, just like a calico cat. Some more really nice pictures of an ARLISS rocket getting prepared to launch. And there's the launch of it. 54 universities attend, 805 student members. Now, in Japan, they have a little bit different than the United States. They have corporations participating in these, supporting them and funding them. So all of the participants in the Japanese is Fujitsu, NEC, Mitsubishi, IHI, Kawasaki, and these other ones. JSAT is Japanese satellite. JSAT is their basically like a NASA, and they support all this. So the Japanese are very aggressive in their space endeavors and satellite endeavors because they also do have a lot of support from the government. As I said earlier, the rocket was a black sky design, and they started using them for rapid acquisition radar tracking. So the modular design was adopted just because of that. And so we kept the rocket was so stable, and we've had, oh gosh, I'm going to say 750 flights of this rocket with only 2 mishaps over the years. So it's just a bomber design. It's fantastic, and you just can't get better than that. Here's a sample of an early avionics bay we had made. We had these aluminum couplers made, and on the side of the rocket right there, you can see an access hatch. So we just cut a hole in it and made an access hatch so that you could get in and turn the switches on and off. So you didn't have to have any switches on the side of your rocket, which means that you couldn't slide the avionics bay in and out. So it's really nice to have an avionics bay that can just slide in and bolt. You don't have to worry about any wires, hooking up wires to switches or anything. And that's just a wonderful way to do it. If you have a 6-inch rocket, it's a good design. Now, if you were going to have GPS, obviously this would be like an I guess you call it anechoic chamber, whatever it is. But you wouldn't get any signal in or out. It would attenuate and it would block all the signals. So you couldn't use this for any GPS. However, we did use it in the ARLISS because we didn't have GPS. We're building a rocket now, which we have this aluminum housing in, and we had to put the GPS in a different location. But it did make a great design. I have a little time left, and I wanted to go over a few things just so your rocketry knowledge. It doesn't have anything to do with ARLISS. So over the years, people have said, what is coning? You know, the coning is a word. Well, it's also called roll, lock in, and lunar motion. So what is it? Here's coning at max Q.
Skies are clear. E4 is armed. Going up in 5, 4, 3, 2, 1. Oh, that did a little curly Q in the sky.
So you can see what happened on that is it started to do coning at max Q and came apart. Coning can amplify itself and get worse and worse. Here's another one.
In 5, 4, 3, 2, 1.
That one happened fast, really fast. That was stress on the fins, coning, and all the stresses
More
that
than that.
Coming down hot.
all the stresses that involve
Skies are clear.
the rocket coming apart.
Coming in hot over. 5, 4.
Okay. Here is another one. Come on, Brad. This is a great one.
Okay, we got Clark, so watch for Clark slopes.
His fins blew apart because of the stress in the coning.
B pads and D pads, and on the
I'll explain coning here in a second, but I just wanted to show you some videos. Here's a great one.
5, 4, 3, 2, 1.
This is a great example of coning. See that? I mean, it even leaves a trail. So the forces weren't violent enough to cause it to fail catastrophically. But those are examples of coning and the bad things associated with it. What is it? It can get real technical, but basically it's when the rocket starts to roll, twist, rotate around, and when the roll rate, let's just say it goes around at 1 roll per second. And if the rocket is trying to right itself, to go off axis, it starts to correct. And when the correction is 1 times the same, when that roll rate and the correction force coincide at the same cycles, the harmonics, that's when it amplifies, and that's when you get the corkscrewing. So the rocket is trying to twist, and it's also trying to go back and forth to right itself. So the twisting, you can see how it will corkscrew. And why is that? Well, long and short of it is because the rocket is not stable enough. Okay, here's some calculations, 7 pages of super analysis, technical analysis of the phenomenon of coning. You might want to write it down as CP Holt, Rocket Sciences and Technology. You can find it on the internet. It goes in depth, and he has all kinds of calculations on the coning. But basically, if you have your, I don't know if I lost it or not, but here we go. If you increase your stability margins, the corrective forces will be less. And if you do have rolling, they won't coincide and you won't get the coning. When the coning starts amplifying, you start getting close to max Q is when it amplifies and you have your shreds. Anyway, that's pretty much the end of my presentation. And I just wanted to thank you for listening in, and hopefully we can get some NAR flyers out there and build some rockets, come out to Black Rock Desert. John Hockheimer is there every year supporting the ARLISS. There's quite a few people out there. Black Rock Desert is not that far. People from all over the country come there all the time. So try to make an effort is get your level 3, come on out and build a rocket, and you get free fuel. So I'm going to end the show and go back into Q&A. And thank you so much for listening in. Okay. Q&As, here we go. How are KATOs handled in terms of team scoring? Stephen, we haven't had any KATOs of motors at all. And the team scoring is done internationally. And the team scoring is basically, I think what you mean by KATOs is when their rover doesn't make it. I don't know how they grade that. I think they have some kind of grading score. What has become of Scott Bartell? I saw Scott Bartell at Tripoli's LDRS last year. Scott was working on some really nice rocket projects, the Artemis rocket, and was one of the engineers on that. He's having a wonderful time. I'm not sure where he's moved to, but he's still the same fun Scott guy we all knew. Justin, what's the best way to get started with the ARLISS program? Is it students only? No. You can be, as long as you're a level 3 flyer, you can build the rocket. If you want to start out on the ARLISS program with building these satellites, please ping me, email me, and I will get that to Becky Green, and she will get you all the information you need. It's open to any student, any high school student, college student, undergrad, grad, whatever. We welcome anybody that wants to do this. There's a lot of scrutiny on this. Now, I don't want to say scrutiny, but a lot of attention given to this. So when you succeed, you rise to the top and you get noticed. And obviously, you can get in line to launch a satellite to space. Add the coning link to the chat for people to grab. Yes. Let me see if I can do that, Ed. Let me do that at the very end. So if I screw up, that'll be the end of it. Scott Bartell. Do you want me to re-talk about that, Ed? Scott Bartell, it says reopen. I don't know, but I can get you information if you'd like to contact Scott, and you might want to reach out to him. Can you attend BlackRock as purely an observer? Yes, you can, and we'd love to have you out there. You mentioned that teams sometimes underestimate the high Gs from parachute deployment. What are some of the other most common mistakes? I'm guiding some CANSAT teams. Okay, SIBO, that's a good question. Under the high Gs from the parachute deployment, the things that we've seen are ground clearance getting stuck, and some of it's just unfortunate luck. You saw that big tire rut. That's usually not out there. And ground clearance is one. The team that I launched from the University of Mexico, when it landed, it jarred some wires loose. So you can get some pretty violent forces when these things deploy, when they land. So I would say strain relief and vibration for all of your components is key. Maybe epoxy them together, I don't know, but there's a lot of failures on that. Not just the parachutes, but just making your electronics and your whole system be, like the, quote unquote, be a systems engineer. Get used to that and make your satellites bombers so that they don't get wires pulled or something like that. Is a chute release allowed? Art, I'm not sure what you mean by that. When they do land, they have to have some kind of mechanism that detaches their payload from the parachute. And I don't know what they use for that. I don't know if they use a line cutter or if it's an electronic device. But if you could ask that question again, I can certainly answer it. Anybody else here? Answered. How are cables answered? Okay. Would you add my contact to chat? Sure. Answer. Okay, there we go. There's my email, so please feel free to email whenever you can, whenever you want to. Please send more messages if you want, and I will get right back to you. Answered. Okay, everybody. Except for Art, I think Art might have a question that I'm still waiting for, but thanks for listening in. And I will post the. Let me see if I can find this. You wanted me to post the. Okay, you wanted me to post the coning link. I can't get to it, guys. I'm sorry. If you want to email me, I will get you the posting link on the coning. I will get you the link. David, chute release. Okay, the Jolly Logic release reefing device that lets you go at baro altitude. I don't think they use that. No. If they did, they would accelerate and they would get going really, really fast. These payloads weigh quite a bit, so your opening shock force would be quite a bit then. The reefing device, it's really not a reefing device. I guess it's just a deployment bag that you hold your parachute in, so it really doesn't create much drag. I mean, it does a little bit, but I'm not sure. I haven't seen a Jolly Logic used on any of these. Yeah. All right, everybody. Thank you so much. And I'm going to stop the broadcast here unless anybody has any other questions. I just posted my email. You see it right down here. tom.rouse@sjsu.edu. And we hope to see some of you out there at Black Rock for the ARLISS launches. It's a lot of fun. Please try to participate with your school in some of these electronics competitions. It's an international event, so you do get noticed. And also try to come on out and build some rockets. Thank you, everybody. Ciao.